Alright, this is section 4.5, Factoring Polynomials. This is Mr. Liao again, and today we will be basically doing some factoring, some basic factoring, but you will be using the difference of squares and some special trinomials. So here we go. How do we factor polynomials using GCF, or greatest common factor? How do we recognize special products? And how do we group terms? So to factor a polynomial, you have to express it as a product of other polynomials taken from a specified factor set. This factor set is generally going to include integer coefficients. Now that's a bunch of words and mumbo jumbo. Let's see how it looks. First, we need to see the greatest common monomial factor, or GCF, of its terms. If there's a common factor other than 1 in all terms, factor it out by applying the distributive property in reverse. And this will be illustrated in number 1. Here, factor 3x cubed minus 15x squared. Excuse me. You are going to look for the greatest common factor between both of those monomials. Now, from what you did on Tuesday in class, you should be able to do this. What's the greatest common factor? Well, we can see the numerical factor is 3. 3 and 15 both are divisible by 3. Both monomials also have an x squared in them, so you can factor both of those out. You take out the 3, you take out the x squared, and what's left is x minus 5 inside. So what you're doing again is the distributive property backwards. You take the 3x squared out and you leave inside the parentheses what's left. So you get 3x squared times the quantity x minus 5. And if you're not sure you got it right, just multiply it back in and see if you get what you started with. Now I mentioned in the previous slide lecture that there are perfect square trinomials that you'll want to remember, both forwards and backwards. And if you want to remember them backwards, it'll make it a lot easier for you to do some factoring. So you're going to use the special products in reverse by identifying them in patterns when you factor. Look to see if the first and last terms are perfect squares. If they are, you might have one of those special products. So if you again look at the perfect square trinomials, a squared plus 2ab plus b squared equals the quantity a plus b squared, and a squared minus 2ab plus b squared equals the quantity a minus quantity squared. So again, you're going to look for the a squared and the b squared, a squared, b squared, and if the middle term is a plus 2ab or minus 2ab, you have one of the perfect square trinomials. Now, of course, it's not always going to say a squared or b squared. It might be 16 or 64, but you should remember that those are perfect squares, and the perfect square trinomials might be applicable. You'll also want to notice the difference of squares. If you have an a squared minus b squared, that can be factored to a plus b times a minus b. So look to see if the first and last terms are perfect squares. If they are, you might have the difference of squares. And again, this is a very helpful thing, so keep that in mind. Example 2, we have x squared plus 14x plus 49. You'll notice that the x squared is a perfect square, and the 49 is a perfect square of 7. Since the middle is 2 times 7, because remember it's 2ab, 2 times 7 times x is 14x. So you do have a perfect square trinomial. When you factor it, you simply factor it as x plus 7 quantity squared. So again, you're going to look for the first and last terms of a trinomial. If they're perfect squares, check the middle term. You might have a perfect square in there. And at some point, you'll want to recognize these quickly, because if you try to factor them the way we're going to learn tomorrow, it might just take you extra time that you don't need to spend doing it. Example 3, factor 81 minus 4a squared. You probably noticed that they are perfect squares, both 81 and 4a squared. What's the square root of 81? It's 9. What's the square root of 4a squared? It's the square root of 2a. So you have a perfect square minus another perfect square. So if you do the a squared minus b squared equals a plus b, a minus b, you get 9 plus 2a and 9 minus 2a. Keeping in mind that the 9 represents the a, so 81 is 9 squared or a squared. 4a squared represents the second term, and 2a squared is 4a squared. And again, if you're not convinced, you can just multiply these out using FOIL and see what you get. The sum and differences of cubes. These are a little more cumbersome to remember, but they will come in very handy, so you'll want to know these as well. You can factor sums and differences of cubes as follows. A cubed plus b cubed equals a plus b times a squared minus ab plus b squared. A cubed minus b cubed equals a minus b times a squared plus ab plus b squared. If you have a hard time remembering this, remember that the a plus b or the a minus b term, the sign matches the sign in the original polynomial. The second sign in the second polynomial, the a squared and the ab, the sign is the opposite. So you see a plus b times a squared minus ab plus b squared equals a cubed plus b cubed. A cubed minus b cubed is the a minus b, and then you have the plus sign here. I wish there was a way to tell you, just remember them, but remember them. Example 4, we have a cubed plus 8. You can try to factor these yourselves, and if you want to stop the video just to practice all these examples, go ahead and do so. You're more than willing and able to do that. Go ahead. So, again, a cubed and 8 are perfect cubes. 8 is the cube of 2. So if we use the pattern, you get a plus b, which is a plus 2, times a squared, which is a squared, minus 2ab, minus ab, here it's 2a plus 4. So once again, a plus 2 times a squared minus 2a plus 4. And if these trip you up, just remember, just substitute a for a and 2 for b and plug them in and then simplify. Example 5. Now we're going to start putting all these ideas together. We have b cubed minus 10b squared plus 25b. The first thing you'll want to do is factor out any common factors. So you factor out the b. When you do that, you're left with b times the quantity b squared minus 10b plus 25. Now again, you'll want to identify that this inside here is a perfect square trinomial of b minus 5. So your answer becomes b times the quantity b minus 5 squared. So you might have to perform multiple steps in some of these problems to get it to its simplest factorial form. Alright, example 6. Now we get to something that's slightly more complicated. We factor xy plus 3y plus 2x plus 6. Now what you're going to want to do is look for common factors between pairs of terms. So if you take a look at this one, and there are a couple other examples on page 185 in the book, you will notice that among the first two terms there's a common factor of y. In the second two terms there's a common factor of 2. And what you're going to look for if you get a problem like this is see what can you factor out such that the two remaining polynomials are the same. So let's factor y out of the first two and then 2 out of the second two, and you get y times the quantity x plus 3 plus 2 times the quantity x plus 3. Now if you notice, all we did is factor out a y of the first two terms and factor out a 2 of the second two terms. Now you have an x plus 3 that's a common factor of both of these. You can factor out the x plus 3 just like you factored out single terms before. So if you factor out the x plus 3 term, you get x plus 3, and what's left inside? Y plus 2. So to do these, you need to again look to see if there are common factors among pairs of terms, and you might have to do a couple attempts because sometimes you'll try it the first time and it won't be the factor you're looking for. If you're given a problem like this on the test or a quiz, you can be sure it's going to be factorable somehow, so you might have to move things around, rearrange the terms, and see what you get. So number 7, factor 16s to the 4th minus 1. These are the problems that are going to require multiple factorizations. So what's the first thing you notice? Go ahead and try these first before you get the answer. So you will notice that you have a difference of squares. 16s to the 4th is the perfect square of 4s squared. And of course 1 is a perfect square of 1. So the first thing you can do is do the difference of squares. If you apply that, you get 4s squared plus 1 times 4s squared minus 1. Well, you're not done yet because the second polynomial here still is a perfect square, a difference of perfect squares. 4s squared is a perfect square of 2s, and 1 is still a perfect square of 1. So you're going to factor the second term a second time. So you're left with 4s squared plus 1 times 2s plus 1 times 2s minus 1. So just because you factor something once, don't assume you are done, because there might be further factorization that you need to complete. Number 8, 2u to the 4th plus 54u. Go ahead and try this one, and resume when you're ready. Alright, the first thing you need to do is factor out the common factors. The 2 and the u are both factors of the two terms. So if you factor out the 2 and the u, you are left inside a u cubed plus 27. Now, again, you will have to identify that u cubed, of course, is a perfect cube of u, and 27 is a perfect cube of 3. So you have to apply the sum of cubes formula. And if you've written that down, you might want to put that in there. So the u cubed plus 27 becomes u plus 3 times the quantity u squared minus 3u plus 9. And you put all three of those things together, that's your final answer. So again, you have to identify sums and differences of cubes if they're there. Look for two terms, and again, it doesn't matter if it's plus or minus, they're both factorable. It's just that the signs are different. Finally, example 9, 4m to the 8th minus 12m to the 4th p cubed plus 9p to the 6th. All right, so we have a lot going on here. Go ahead and try this one and come back and check the answer. All right, first thing you'll notice is that 4m to the 8th is a perfect square of 2m to the 4th. 9p to the 6th is a perfect square of 3p cubed. So the middle term also matches because it's 2 times, or negative 2 times 2m to the 4th and 3p cubed. So when you factor that, you get 2m to the 4th minus 3p cubed quantity squared. And you can't really factor that anymore. You don't have a difference of squares. You don't have a difference of cubes or sum of cubes. So that's your final answer, 2m to the 4th minus 3p cubed quantity squared. There are additional practice problems in the book on page 184 and 185. The book has additional examples if you still need extra help. If you have any questions, write them down, put them on Facebook, or email me, and we'll talk about it in class the next day.